Hello, welcome back to EEforEveryone. Today we're going to bring it back to the basics, talk about something that's really simple from a 10,000 foot view. However, when you dig into the details, a tolerance isn't as simple as you might think. The complexity of tolerance is the main reason why defining good requirements is essential before diving into detailed design work. A good requirement will define the expected operation and the conditions under which the system should achieve that operation. That's a lot of words, but requirements do seem like an awful lot of work, right? Like, I'm asking you to take 3 or 4 days to hammer out exactly what the system should do before you even start designing. Those are precious days that could have been spent actually building the thing. Yeah, sure, maybe, but what if you finish building something and then it doesn't meet your requirements? Ultimately, there's still some bar by which your design will be measured. Then you need to go through and design something twice. Now, building something twice will probably take longer than defining good requirements and building it once. We've talked about the common emitter amplifier circuit a few times now and mentioned how it operates. I want to use this circuit as an example of how difficult it can be to achieve a tolerance over a variety of test conditions. Let's say that the requirement is written as, this common emitter amplifier shall have a gain of 4. Fine. This configuration on the screen achieves a gain of 4. Great. We have a gain, or amplification factor, of 4. Now that we've achieved such a great accomplishment, we build 100 of them and ship them into the world. But we keep getting reports that the amplifier doesn't have a gain of 4. We have reports of people supplying 5 volts instead of 12, reports of people inputting signals with an amplitude of 20 volts and expecting to see 80 volts on the output, and people who attached a 10 ohm load to the output and didn't get the amplification factor they were looking for. Oof. That's a lot of unhappy people. Before we tell them all that they're dumb and the design works, let's test our amplifier under these conditions. Let's start with the 5 volt supply voltage. We plot the input, which shows exactly what we would expect, now the output, and flatline. The signal appears to be completely destroyed. How can that be? The circuit worked fine before. Let's dive deeper, looking at the base current and collector current. Oh, the base current is almost completely gone. Centered around 0 with an amplitude of 2 nanoamps, that's not great. In fact, the transistor would be considered off. The collector current is about 20 nanoamps peak to peak, and that's barely any variation at all. The signal is coupled through C3, and eventually the few microvolts is passed to the output. Looks like that customer is rightly upset. This was sold as a 4 times amplifier, and this didn't amplify at all. What about the 20 volt input? Sure enough, the input voltage is a 20 volt peak-to-peak sine wave, and the output is confusing. There's clearly a lot of clipping going on here, since the input voltage is larger than the supply voltage, but the voltage at the base of the transistor is negative in the steady state, and this whole situation is pretty confusing. This kind of reverse bias on the base emitter junction, it's safe to say the transistor wouldn't last long. This amplifier probably met an untimely end in the field. I think you can imagine that the amplifier with the 10 ohm load doesn't perform as expected either, but I'll show you what happens anyways. The input is normal, and the output is less than the input. The gain dropped from 4 to about 0.5. That's also not great. How do we fix this? How do we build an amplifier that meets the needs of the people who want it? First, we need to define the supply voltage, input signal amplitude range, and output gain tolerance. We'll say that with a 12 volt input voltage, the amplifier will have a gain of 4 plus or minus 5%. For input signals with an amplitude less than 50 millivolts 0 to peak. Even this is open to interpretation since the frequency isn't considered. If a person were to apply a signal with a frequency of 0 Hz, this amplifier wouldn't respond at all. Plus, noise on the voltage rail directly couples into the load, so we need to determine the maximum allowable ripple on the input voltage. This brings our statement to, with a 12 volt input voltage having a maximum ripple amplitude of 0.1 volts, the amplifier will have a gain of 4 plus or minus 5%. for when an input signal of no more than 50 millivolts 0 to peak is applied over the frequency range of 1 kHz to 1 MHz. That's a lot different from our original statement, but we aren't done yet. Transistors are not rated for operation at every temperature, and the gain of a transistor varies quite a bit over changes in temperature. In fact, the resistance of our resistors and the capacitance of our capacitors will also vary over temperature, but we still aren't done. The resistances, capacitance, and properties of the transistor can also change over time. We need to make sure that our design will meet that 5% specification over its lifetime in a specific temperature range at every rated frequency. Before we dig into all that, because this conversation could snowball into a 3-hour lecture, let's start with the basics. The initial tolerance on every component. There are 4 resistors in this design, all of which have a 1% tolerance. We know that RO being a maximum and RE being a minimum will maximize the gain. We know that R1 being a minimum and R2 being a maximum will increase the DC offset at the collector of the transistor. As long as this doesn't cause clipping, it won't affect the gain. However, the HFE will affect the gain directly, as long as the capacitor value isn't such that it's attenuating the signal. Then it'll have very little impact on the gain. Now, we can calculate or take all those parameters out of the datasheet for the components and calculate the maximum possible gain with our component tolerances in mind. This type of mentality, where the extreme values of every component line up just wrong to maximize the parameter being considered, is called extreme value analysis, or EVA. This is very conservative since it's very unlikely that every component in the circuit will line up just perfectly wrong. However, it is possible that it could happen, and the circuit will certainly never have a gain more than it would in this case. RSS is another methodology that is more computationally difficult, but closer to what would happen in real life. When we look to evaluate the minimum possible gain, we would minimize HFE, maximize RO, and minimize RE. If the minimum possible gain and the maximum possible gain are still within the 5% tolerance, then we can be confident that with any smattering of resistor values between the extreme values possible, our circuit will meet its specifications. Achieving a specific function across all possible operating conditions such that if you built 3 million units they would all pass, foregoing any manufacturing defects, is a very difficult task. This is a difficult task for even a seemingly trivial circuit. Ultimately, there comes a point where it will cost more to analyze the design further than it will to throw out a board out of 1,000, and then you stop considering every possible variable. A combination of careful analysis and experimental results is usually the best approach to minimize risk. However, when human life is on the line, or it would cost $1 million to change a resistor, sometimes it is required to fully analyze the worst possible operation of a system. When failure to meet a specification in 1 out of 1 million units is simply not an option, you just have to put in the time and do a worst-case analysis. Keep an eye out for some future videos where we'll talk about worst-case analysis and derating, which are really a continuation of this discussion. If you think that achieving a tolerance in every circumstance is cool and this video is great, let me know by hitting the like button on this video, subscribing to the channel, and leaving a comment letting us know what you enjoyed. Most of all, I hope that you learned something great today, and I hope to see you again soon. Bye!